Chapter 17 is on aldehydes and ketones. Aldehydes are compounds containing a carbonyl group attached to a hydrogen, and then the carbon in the carbonyl group can be attached to either an alkyl group, an aromatic group, or another hydrogen, as shown below here. This is our carbonyl, which is a carbon double bonded to an oxygen, and to that carbon we have a hydrogen attached. This makes the functional group, the aldehyde. The R stands for either the alkyl group that's attached to that carbon, or an aromatic group, or another hydrogen. Some examples are shown below. So in the first one, here is our functional group for our aldehyde, and then this one is attached to an alkyl group to that aldehyde. The second one here, we have our aldehyde functional group, and then we have a hydrogen attached to that carbon in the carbonyl. The one at the end, we have our aldehyde functional group, and it's attached to an aromatic compound. The compound at the end here is called benzaldehyde, and this is the smell that's in almonds. To name aldehydes, you will follow the same rules as alkanes with a few additional rules. Your longest chain must include the aldehyde group. The suffix al represents the aldehyde group. You'll replace the ending E with al. So these are very similar to naming alcohols. With the alcohol, you had the ending ol. This one is going to be the ending al, so it's very similar. So in our example here, we have methane when we have one carbon with all single bonds to hydrogen. If we have one carbon that has our functional group, the aldehyde, to change the name, we would drop the E and add the ending al. So the name of our compound would be methanal. Common name is formaldehyde. This is an embalming fluid that you may have smelled in a biology lab. Name this compound. The compound on the left is called ethane because we have two carbons with all single bonds to hydrogens. The one on the right, we also have two carbons, but we have our functional group, the aldehyde. So to name that, we're going to drop the ending and we would add al. So the name of our compound is ethanal, not to be confused with ethanol, which is also two carbons, but it's the OH that's attached, your hydroxyl group, that makes it an alcohol. So the difference here is OL versus AL that makes them two different functional compounds. We also learned about ethanol. When it's oxidized in your body, it decomposes into ethanol. And this would further break down into other compounds that you could excrete out of your body, such as carbon dioxide and water. We learned about the drug called antabuse that would actually stop the reaction at this point, and the buildup of ethanol in your body, its common name is acid aldehyde. You don't have to remember the common name, but the buildup of this in your body causes the nausea and vomiting. Name this compound. So we have three carbons in our parent chain that is attached to our functional group, the aldehyde. So three carbons gives us the prefix prop, and the ending, if it was all single bonds to hydrogens, would be propane. So since there's an aldehyde, we would drop the E in propane and add Al. So the name of this compound is propanal. Please note, no number is needed in the name to identify the location of the aldehyde group, because the aldehyde group is always going to be located at the end of the chain. Rule number 3 states, if groups are attached to the parent, assign the lowest possible number to the carbon attached to that group. So first thing is we want to name the parent. Our longest chain of carbons that's attached to our functional group, the aldehyde, is a total of 1, 2, 3, 4, 5. So the name of the parent is pent and al. And then what this rule is saying is we have a group attached. It's called an ethyl. And we want to assign the carbon that's in our parent group to have the smallest number. So the carbon number 1 has to be where the functional group is. So when we count right to left, that's going to be attached at carbon number 2. So we would write the group or the child in front of the parent. We have ethyl pentanal, and it's attached at carbon 2. So the name of our compound is 2-ethyl pentanal. Ketones are compounds containing a carbonyl group attached to 2 alkyl or 2 aromatic groups, or 1 alkyl and 1 aromatic, as shown with the general formula here. So here is our carbonyl, carbon double bond to oxygen. The R's on both sides of the carbon attached to the carbonyl could either be alkyl groups or aromatics, or a combination of the two, as shown in our examples below. The first example, we have our ketone functional group. The carbon attached to the carbonyl has alkyl groups attached on both sides, represented by CH3. The compound on our right, again, we have our ketone functional group. We have carbon double bond oxygen, and it has carbons on both sides of the carbon attached in the carbonyl. And in this case, we have an alkyl group or a methyl group attached on the right, and then this one has an aromatic on the left. To name ketones, we'll follow the same rules as alkanes with a few additional rules. The longest chain must include the ketone group. The suffix -one represents your carbonyl group. You're going to replace the ending E with ONE or -one. So for example, we have 3 carbons. For our alkane on the left, the name of the compound would be propane. The one on the right, we have the functional group, the ketone. We have 3 carbons. So we're going to take the word propane. We're going to cross off that E and add -one. So the IUPAC name of this compound, following our rules, is propanone. The common name you may have heard of before is called acetone. Acetone is what's in a lot of nail polish removers. There's a question here. Can you have methanone? Well, meth means 1 carbon. So if we have 1 carbon, the ending -one means it's a ketone. But ketone means we need to have carbons on both sides. Methanone says there's only 1 carbon, so we would not be able to have methanone. What about ethanone? Eth means 2 carbons, so we could have carbon double bond to oxygen for our carbonyl and a carbon on one side. But on this side, we only can have 2 carbons, that this would not exist either for ethanone. So you need to have a minimum of 3 carbons in order to have a ketone. Rule number 3 says if 4 or more carbons are present, assign the lowest possible number to the carbon attached to the double bond oxygen in the parent chain. So in our first example, we have a total of 5 carbons. So 5 would be pentanone because we have that ketone functional group. And then we want to show when we have 4 or more carbons in your parent, the location of where the double bond to the oxygen is. So if we count from left to right, that would be attached at carbon 2. If we went from right to left, it would be at carbon number 4. So we want to go with the red numbering and have it be attached at carbon number 2. So this compound would be called 2-pentanone. So you can take note that the carbon attached to the double bond oxygen will never be carbon number 1. The next example on the right, we look at our longest chain of carbons attached to the double bond of oxygen, and we can count. In this case, we have 1, 2, 3, 4, 5, 6. So our parent is hex, unknown. And then we want to show the location of where that double bond is. Which carbon is it attached to? So if we go left to right, it's at carbon 3. If we were to go right to left, it would be at carbon 4. So we want to go with the red numbering. I'm going to delete the blue. And that's attached at carbon number 3. So we have 3-hexanone as our parent. Now in this example, we have a group attached at carbon number 5. So we need to name our group bromo in front of the parent, and then we put a number 5 to show the location of which carbon our bromo is attached to. So the name of our compound on the right is 5-bromo-3-hexanone. Name this compound. So first thing, we find the longest chain of carbon that includes our functional group, which we can see is a ketone. So my longest chain of carbons goes straight across, and if we count from right to left, we can see that we have a total of 6 carbons. So the parent is hex, unknown. We want to show at which carbon is the double bond oxygen attached at. So again, if we go from right to left, we can see it's at carbon 2. If we were to count left to right, it would be at carbon 5. So we want the smallest number possible. So we can put 2-hexanone, that's the name of our parent. Now in this example, we have some groups attached. The first one we have is Cl, is called chloro. The second group we have, CH3, is methyl. Now, if we have 2 groups attached or 2 children, we put them in alphabetical order. So chloro will come first, and then methyl. And then we need to show the location of our 2 children, and they are both attached at carbon number 5. So we'll put a 5 in front of chloro and a 5 in front of methyl. So the name of our compound is 5-chloro-5-methyl-2-hexanone. Name this compound. Let's count our longest chain of carbons that includes our functional group, the ketone. So going straight across, we have, if we count from right to left, 1, 2, 3, 4, 5, 6, 7. So the parent for 7 is going to be heptanone. And then we want to show the location of the carbon where the double bond to oxygen is attached. That's going to be at carbon 3 if we count from right to left. If we were to go from left to right, we would see it's at carbon 1, 2, 3, 4, 5. So we don't want to use the red numbering, because then our carbon would be at a larger number. So we always have to go with the smallest number. Now in this example, we have groups attached. 2 groups that are the same. It's called a methyl group for CH3. So if we have 2 of the same groups, we write dimethyl. And then they're both attached at carbon number 6. So we can write in front 6, 6, dash, because you have to show the location of both of those methyl groups. So the name of the compound is 6,6-dimethyl-3-heptanone. Name this compound. So our longest chain of carbons with the functional group is straight across the middle, and we're going to count how many carbons we have. We're going to count from right to left, and we have a total of 5 carbons. Now the functional group in this compound is we have an aldehyde. So with 5 carbons, we have pent, tan, and then we add Al for aldehyde. And with an aldehyde, carbon number 1 is always going to be where that aldehyde functional group is. So we don't have any other option the way we would write the numbers. So then our groups we have attached are 2 fluorines. And when we have 2 of the same group, we put a di in front to represent that. So difluoropentanal. And again, realize there's no number required in front of pentanal because the carbon where the aldehyde is always going to be carbon 1. So no number is needed there. And then we want to show the location of our 2 fluoros. One is at carbon 3, the other one is at carbon 4. So we add those in front of our children's name. So the name of our compound is 3,4-difluoropentanal. Let's review functional groups by circling and naming the functional groups in the following 2 compounds. So the one on the left is called vanillin, and some functional groups we may notice are the one I'm circling here is a carbon double bond to an oxygen, and then we have a hydrogen attached to one of those carbons. That makes an aldehyde. And then we previously learned if we have a carbon bonded to an oxygen bonded to another carbon, that makes an ether. And then we have one more functional group in this compound. We have an aromatic compound. So we have a benzene ring that's attached to a hydroxyl group. That is called phenol. So this compound, vanillin, has 3 functional groups. And you know the smell from vanillin is going to be vanilla. The compound on the right, we have a carbon with a double bond to oxygen, and this one has carbons attached on both sides of it. So that makes this one a ketone. And this compound also has 2 more functional groups. Carbon double bond to another carbon is a alkene. And then in this one I have another carbon double bond to a carbon. I have a second alkene. And this compound is called ionone, and this is actually the smell in violets that is used sometimes in perfumes. Circle and name the functional groups in the following compounds. I'd like to go ahead and draw in some of our carbons in these line angle drawings, just so it's clear that you can see where all the carbons are. So let's start with the one on the left. So one of the functional groups I see in this compound is I see a carbon double bond to oxygen, and it has a hydrogen attached to that carbon in the carbonyl. So here we have an aldehyde. And then I have a carbon double bond to another carbon. That's my alkene. And then I have this benzene ring attached to that. So that is an aromatic functional group. The one in the center, I have a carbon double bond to an oxygen, and this one has carbons on both sides of the carbon in the carbonyl, so that makes this a ketone. And the one on the far right, I have a carbon attached to a carbon with a double bond to an oxygen, making a ketone. And this one actually has a second ketone as well. Carbon double bond to oxygen with carbons on both sides. So these are compounds you may see in your everyday life. The first one on the left is called cinnamon aldehyde, and that's the smell in cinnamon. The one in the center here is found in musk deer. That's this odor musk is often used in colognes or perfume. And then the one on the right is the flavoring that's used in margarine. Aldehydes can undergo oxidation reactions. Ketones do not undergo oxidation reactions. So an aldehyde can be oxidized by a number of different oxidizing agents. A review as an oxidizing agent, here it's represented by oxygen in the brackets, is a compound that adds oxygen to your reactant or causes the loss of hydrogen. Oxygen in the air is a mild oxidizing agent. So aldehydes can actually be oxidized by oxygen in the air, so they should be stored in airtight containers. So aldehydes are oxidized to form carboxylic acid. As review, a carboxylic acid is a carbon with a double bond to oxygen, and that's attached to an oxygen bonded to a hydrogen or a hydroxyl group. So I do want you to remember that aldehydes, when they react with an oxidizing agent, will form carboxylic acids. Ketones, however, do not undergo oxidation, so there is no reaction. There are different types of oxidizing agents. One example of an oxidizing agent that will oxidize an aldehyde is called Tollens reagent. Tollens reagent contains silver nitrate and ammonia in water, which would be symbolized by that compound. So here we have an aldehyde. It undergoes oxidation to form a carboxylic acid. The other product it makes is silver and ammonia. So this is actually how they produce the silver in mirrors. They used to use it more in industry, but silver's pretty expensive for the silver nitrate solution, so it's not as commonly used, but it is still used in order to make silver mirrors. This is showing you in a laboratory if you were to do the test tube reaction. Your silver nitrate ammonia water solution is clear, and then when you react with the aldehyde, which is also clear, this is an intermediate where it looks kind of cloudy, and then in the end you form the silver you see lining the inside of the test tube. So this is actually kind of a fun reaction to do. Benedict Solution is another oxidizing agent that will react with aldehydes. Benedict Solution contains copper ions in a basic solution. The copper ions actually give the solution a blue color. So this reaction is showing our aldehyde reacting with Benedict solution, and it's undergoing oxidation to form a carboxylic acid. So you can see the aldehyde's oxygen is being added in order to form the carboxylic acid by our oxidizing agent. You also form copper 1 oxide, and you can get either a green or an orangish red color for an observation if you did this reaction. So this is one of the experiments we do in the laboratory, and a positive test, meaning your aldehyde reacts and it's oxidized, is the blue color will disappear and you're going to form either what you would observe a green or a reddish orange color, which is shown in these test tubes down below. Now a ketone, if you reacted it with the Benedicts, nothing would happen. So what you would observe is the blue color would stay blue. So that's how you would know that you had a ketone. And if you had aldehydes, your aldehydes, you would see a color change. Complete the following reactions by drawing the structural formula of the organic product formed in the reaction. So the first compound we have here is our aldehydes. So we learned Benedict's reagent, it's an oxidizing agent. You don't need to remember the formula, but just realize I'm adding an oxidizing agent to an aldehyde, so it's going to undergo oxidation and form a carboxylic acid. So the number of carbons is all going to remain the same. So I'm going to draw my carbon chain here, and I have a total of 1, 2, 3, 4, 5. So I'm drawing 5 carbons in my parent chain. And then we're forming a carboxylic acid. So the double bond to the oxygen stays the same. And so all we've done is added an oxygen between the carbon and hydrogen bond to form our carboxylic acid. So structural formula means show me every bond. So I'm going to go ahead and add all my hydrogens in and show me all the bonds between my carbon and hydrogens to get my final product. So again, undergoing an oxidation reaction for aldehydes, you will form a carboxylic acid. So be able to complete these types of reactions. And I wrote in the problem organic product because you don't have to worry about what happens with the Benedict reagent, the actual formula of what it forms. But do know the color. Benedict's is blue. And when it reacts to form a carboxylic acid, this could be, either green or like an orangish red color. The one at the below, we have our functional group, and this compound is a ketone. And we said ketones, when you react them with your oxidizing agent, Benedict solution, they do not react. So this one would be no reaction is what you would write for your product. And in this case, if you were in the lab, what you would visually see is I add my blue solution, my solution stays blue. There's no color change.